So do you want to enter the presentation mode? David?
What?
So on my side, I saw a small window. It's not in presentation mode.
No, I haven't put it on play.
Oh, okay. I see.
How does that look?
Oh, okay, perfect.
Perfect.
So then shall we start? So today we are very glad to have Professor David Kaplan from the University of Washington, who will tell us about domain warp fermions and Chiral gauge theories. So please start.
Okay, thank you. Well, thanks very much for inviting me. Today I want to talk a little bit about some of the fruitful areas for cross-fertilization between particle physics and condensed matter physics. There's a long history here, of course. Here I just showed three great figures in that process. Rudolf Peierls took Dirac's particle hole theory and applied it to condensed matter physics with great results, like the transistor eventually. Nambu stole a bunch of wonderful phenomenology from superconductivity and was able to understand features of the strong interactions by showing how chiral symmetry breaking occurred in the strong interactions, similar to the way Cooper pairs condense in superconductivity. And Wilson completely transformed how we think about quantum field theory by forcing people to think of regulating quantum field theories the way condensed matter systems work with a lattice, and completely turning on its head how we view marginal versus irrelevant operators. The problem is that there's a lot of language problems, a lot of different ways of thinking about things. The question is, can we communicate and share some of the insights? Too often, I think people view members of the other field as aliens. And so I think in the last decade, there's been a lot of progress in developing a common language. So what I'm going to talk about here is some of this overlap between relativistic quantum field theory, in particular the issue of chiral symmetry with fermions, along with on the condensed matter side, quantum Hall physics and topological materials, of which I'm the first to confess that I'm not an expert. So I may say some stupid things, and I hope you'll forgive me in the spirit of this talk, which is to try to promote communication between the two sides. So the topics are going to be the Nils and Anemia theorem, chiral symmetry and domain wall fermions on the lattice, the connection of these relatively old ideas to topological insulators and quantum Hall effects. And then I will try to talk about some opportunities for cross-fertilization, again, more connections between the two, but also open questions that maybe could be answered with expertise from one side or the other. This includes discussion about the overlap operator, some fractional quantum spin Hall effect, but then ultimately the big question I think is, how do we understand chiral gauge theories? So let me start with an old problem, which was the Nils and Anemia theorem, which was formulated in 1981, which said that if you want to formulate fermions on a lattice with some sort of action with a derivative type, a Dirac type operator, here I've shown it in momentum space on a Brillouin zone where A is the lattice spacing. They show that you could not have simultaneously all four properties which you may have thought were desirable. One is that this D operator is periodic and analytic in momentum, that it has a continuum limit that looks like the Dirac operator, it is invertible everywhere except for p equals 0. I should mention this is Euclidean spacetime, so a pole at p equals 0 is what you would expect for a massless particle. And that there exists a gamma matrix, which in 4 dimensions is gamma 5, which anticommutes with D. So the first point, locality is important. An example of a propagator that failed this was the slack derivative, where they wanted to have a sawtooth form for D of P. It was discontinuous at the edges of the Brillouin zone. And the way I think about the problem that appears there is that we know the word identity tells us that the coupling of the photon is proportional to the derivative with respect to momentum of the inverse of d. And therefore, the word identity tells you that at the points of discontinuity, you're going to have infinite, or at least some totally strange photon coupling. And so modes at the edge of the Brillouin zone won't decouple the way you might expect. That was found for the slack derivative. The second term just tells you that you only want one flavor, and it has to look Dirac at long wavelength. The third one tells you that the second one says it has to look at Dirac at long wavelength. The third one says you don't want extra flavors. You only want one fermion. And the fourth says it respects the chiral symmetry. Now, I should note that this gamma is only something you would expect to be able to define in even space-time dimensions because of the properties of the SON groups. So the way I like to think of the Nils-Anemia theorem is not so much in a mathematical language, but in a physical language, which is that it's sort of required by anomalies. If you look at a massless Dirac fermion in the continuum in 1+1 dimension, then you have right-handed modes and left-handed modes. And the vacuum serves, Dirac C serves as an infinite sink or source for fermions. And so when I turn on an electric field in the direction of the wire, you start pulling out, if they're positively charged, you start pulling out right-handed fermions out of the vacuum, you start pushing left-handed fermions into the vacuum. And when you compute the change in time of the number of right minus left, you find that you get something proportional to the electric field. And in fact, this reproduces correctly the 1+1 dimensional axial anomaly. Note that in this process, of course, the net number of charges does not change. And so charge is not violated as you would expect. So the principle here is the Hilbert Hotel, where you're bringing in a bunch of visitors, say left-handed fermions being pushed into the vacuum, and there's no problem accommodating all the new visitors because everybody in the hotel just moves over one. And so that's what's going on in the vacuum in the continuum. But on the lattice, the whole point of lattice quantum field theory from the point of view of a high energy physicist is to cut down the Hilbert space from infinite dimensional to finite dimensional, so you can put it on a computer. And of course, when you have a finite dimensional hotel, if you stick guests in one side, they pop out the other. So that suggests that the anomaly is not something that is easily reproduced on the lattice. And in fact, we know that another way of thinking about it is in the continuum, anomalies arise from the Jacobian of an infinite matrix, according to Fujikawa. But of course, there are no infinite matrices on a lattice theory with finite volume. And so all of the classical symmetries are good quantum symmetries. And so if you want to have a lattice theory that reproduces an anomaly in the continuum, that symmetry must be explicitly broken on the lattice. So how do various fermions conform to the Nils-Anemia theorem? Well, the simplest thing is the naive fermion discretization, where you just do a forward-backward derivative. This one, of course, gives rise to a propagator that looks like this, where if I take A goes to 0, then I see 1 over P slash, as I hope for Dirac fermion. But I also see poles at the corners of the Brillouin zone when any of the P's is an integer times pi. So you get multiple flavors. Furthermore, if you look at where the flavors are sitting and you analyze their chirality, you find that even though you do have a good gamma 5 matrix on the lattice, you find that the continuum modes have alternating chirality, so that in fact this gamma matrix corresponds to a vector-like symmetry in the continuum and is not the chiral symmetry you're hoping to find. Wilson fermions instead introduce this extra term here, which in a continuum language looks like that. It's a dimension 5 operator, so it's irrelevant. Therefore, it should not affect the IR physics, but it does get rid of the modes at the edges of the Brillouin zone. It's also easily gauged, where you replace the ordinary partial derivative by the lattice gauge derivative. It's important, though, that this extra term here has the same chiral properties as a mass term and therefore violates chiral symmetry. So it gets through it conforms to the Nils-Anemia theorem by it gets rid of the poles. So you no longer have the problem of the naive fermions, but now you don't have a gamma 5 matrix in the theory. Well, So if you look at the spectrum, this is what the spectrum of a Wilson fermion looks like of energy versus momentum. And you can see here that if I want to close that gap, I'm going to have to fine tune this R against this M. Both of them are going to be order 1 in lattice units. And you can do that. However, the theory is explicitly breaking the U1 axial. And you find that as you do the fine tuning, the breaking of the U1 axial does not go away. And in fact, you will, when you go to the limit you want, you find, in fact, that you retain the U1 axial breaking and correctly reproduce the U1 axial anomaly. Unfortunately, this is a crude tool, and you also break all sorts of other symmetries. Like if you have 2-flavor QCD, you'd like to have an SE2 left cross SE2 right chiral symmetry. That is the symmetry that explains the lightness of the pions, for example, but this Wilson term breaks that too. Now you can fine tune it and make the pions massless, but when you start asking about, say, 4 fermion operators from the weak interactions, you want to study CP violation or something, every operator has to be tuned, and it becomes a rather arduous task if you are looking at a process that is very sensitive to chiral symmetry. So this is a theory where fermions get an additive master normalization. They're sort of like, they behave like the Higgs in the standard model. It's disturbing that they're so light. So you have to work at it.
Excuse me, David?
Yeah.
Just make sure. So the chiral symmetry here is realized in a way not strictly local, is that right? So quasi-local, non-on-site in non-on-site in condensed matter sense. Maybe so, quasi-local.
Yeah, so that's a good question. I'll get to that when I talk about the Ginzburg-Wilson equation. Because you're right, if you tune this, then what's going on? I have a lattice theory. I've got chiral fermions, and yet I have an anomaly. So it's not completely chiral. So the question is, what is the lattice fermion getting in this limit? And so we'll get to that in a second.
David, may I ask a question? Sorry, this is Andrzej Wiadomski. I'm a condensed matter theorist, and pardon me for the naivete, but if the statement you made is that the way the Wilson fermions get around the Nils-Anemia theorem is by having this force constraint. So what do you mean that they're not chiral, or they don't commute with?
They're not chiral because this extra term here violates chiral symmetry. So there is no gamma matrix that commutes with this operator, no gamma 5 that anti-commutes.
And that's just a mass, correct? That's just a mass term.
Right, and it goes along with a gap here because in general, you need a chiral symmetry to protect you from getting, you need a chiral symmetry to make it gapless, or else you need fortuitous fine tuning.
Right, so if you don't set A to 0, what would happen? You're saying that if you close the gap, then Nils-Anemia theorem still holds. Like, yeah, that example over there, what does that say?
So this is a limit where you're taking the continuum limit and tuning M against R at the same time. Okay, and nowhere along the path until you reach the limit do you have chiral symmetry. And so the non-decoupling of the U1 axial anomaly is sort of a subtle effect. Okay, but you're never looking at a lattice theory with an exact chiral symmetry.
Excellent, thank you.
Okay, but it still begs the question about when you tune close to something like this on a lattice, what's going on, okay? And we'll get to that in a moment. In fact, right now. So it's clear that you'd like to have a fermion operator with enough chiral symmetry violation to explain the anomaly, but no more, okay? And what I mean by no more is that you want to preserve the feature in the continuum that you love, which is that fermion masses are only multiplicatively renormalized and not additively renormalized. So Ginzburg and Wilson said, well, how could we do that? And they came up with this following very interesting equation, which says, rather than looking for a gamma matrix that anti-commutes with D, so assuming that all the other 3 points of the Nils-Anemia theorem are satisfied, and therefore the chiral symmetry cannot be, let's look at this following form of violation of chiral symmetry. Let's put on the right-hand side, rather than 0, which would be the continuum expectation, let's put on something proportional to the lattice space and that goes away in the continuum that looks like the same D matrix times gamma 5 times D. Now, this looks completely ad hoc and strange, but it is immediately possible to see why this works heuristically. The chiral ward identities are time-ordered products of the divergence of the axial current with a string of operators. The chiral ward identity says that if you take the derivative of this thing, you'll get 0 unless J mu 5 is sitting right on top of one of the other operators. And if it is, that's where the anomaly comes from. So if you take the chiral ward identity and you replace the divergence of the axial current by the right-hand side of the Ginzburg-Wilson equation, you have A d gamma 5d sitting at this vertex. But remember that the Fermion propagator is d inverse. So this d is sitting on both sides of the vertex and cancels these two derivatives. So if you're working in space, then it gives you delta functions in space, which means that this vertex has to be sitting at the same point as an operator in this gray blob on both sides. And so this will give you 0 unless you have a current which is sitting on top of other operators. And that turns out to be enough to ensure that you get multiplicative mass renormalization, and it's enough to reproduce the anomaly. You might ask, how in the world did they come up with this equation? The answer was, I'll show you in a moment, but the point is this occurred in 1984, but it was a dead end for a long time. They got almost, I don't know, 6 citations in a decade because they could not find a D that obeyed this equation. They said, if you could find a D that obeys this equation, you're in gold. You've got exactly what you want, but they could not find a solution. Now, just quickly to explain how they found the solution, it was really clever. They started with a chirally invariant continuum action with chiral invariance up to anomalies, which represented through the Fujikawa method through the Jacobian. They then performed block spin transformation to turn it into a lattice theory. So they went the opposite direction. They went from a continuum theory to lattice theory by defining a new variable chi, which was an average over the continuum fermion over a cell. This averaging, which they did through this Gaussian, explicitly broke chiral symmetry, but they're just introducing a new variable and they're going to integrate over it. So it has no effect on the physics. But if you now reverse the integration and integrate over psi instead of chi, then you get a lattice theory, which you know has all the same chiral symmetry as the continuum theory. So they were able to perform that integral enough to show that you got a D that obeyed the Ginzburg-Wilson equation without being able to solve for what that D was. So it was pretty clever. Now, an unrelated series of events in the mid-80s, Callan and Harvey, building on work by Jakiv and Rebbe, they wanted to come up with a physical model to explain some rather mathematical results by Zumino, which related chiral parity and non-abelian anomalies in different dimensions. The work by Zumino was very mathematical and didn't seem to have a clear picture of what was going on. So Callan and Harvey constructed a physical model where they said, let's have a fermion, let's take in 3 dimensions, 3 space-time dimensions, and let's give it a mass that has a step function. So on one side, it's plus lambda, and on the other side, it's minus lambda. And then from the work of Jakiv and Rebbe, they know that on this infinite plane, there exists one left-handed mode that lives on the defect. Now, you might ask, well, how in the world did a node make it left-handed instead of right-handed? And the answer is that in 3 dimensions, 3 space-time dimensions, a fermion mass violates parity. And so there's parity violation built into the system. And with some sign conventions about what you mean by gamma 5, you'll only get 1 chiral mode on the defect. Now, it's also true if you take a half space. They didn't have to take a step function. And this is something with the correct boundary conditions. And we'll get into that later a bit. So they then said, well, this seems like a problem because when you turn on an electric field, you're going to have a anomaly, and you know that the charge on this defect has to either grow or fall, and yet the whole 3-dimensional theory has no anomaly. So where's the charge? The charge has to be conserved somehow. So where's the charge coming from? So they showed that it's compensated by a Chern-Simons current in the bulk. So what happens then was you turn on an electric field, these modes get pushed down into the vacuum, but the extra current, which you need, the extra charge, which you need to give or receive, goes off into the bulk. Now that's pretty surprising because there are no light modes in the bulk. It's gapped. All the masses are set by the scale lambda. Just as somewhat technical side effect, but which will play a big role when we go to the lattice, is the one thing they forgot was that since when they computed the Chern-Simons current, it was finite, they ignored the regulator. The regulator, however, doesn't decouple and gives you a constant effect here, does not have a domain wall mass. It gives a current contribution that's just constant across the lattice, so it doesn't look very interesting, but it will have a big effect when we talk about the lattice. But the upshot is that there is no current on one side and twice what they said on the other. So Cowan and Harvey had half a unit of charge coming from each direction and said you get 1 unit from one side and 0 from the other. That'll be important when we consider the topology of what's going on. So the way they computed this is they said, well, let's just integrate out the heavy fermions in the bulk, and let's pretend that the mass is completely uniform on one side, and then with one sign, and we'll compute the mass on the other. And so they get 2 contributions that, if they include the regulator. One is from the particle with the step function. So you get these Chern-Simon operators, either this is the abelian case, but you can do it for non-abelian gauge fields too, and 3 spacetime or 5 spacetime dimensions. And then the coefficient goes like m over that value of m, which for the regulator is just a 1 or -1. But for the step function fermion is a step function itself. And it's really critical and interesting that these heavy fermions in the bulk do not decouple. This coefficient does not go away as the mass goes to infinity. Now, if you differentiate these operators with respect to the gauge field in the bulk direction, you find you get a current in the bulk direction, and its coefficient is given by this step function plus shifted step function, times something that looks like the, in this case, 2-dimensional electric field. And sure enough, this gives you the anomaly, and it's this current, since it has a step function, is either flowing into the wall or out of the wall, or in on one side or out on one side. And so it has a non-zero divergence. And when you compute the divergence, it exactly accounts for the anomaly. So this is how they were able to explain the Chern-Simons term, which is related to the parity anomaly in 3 spacetime dimensions, to the chiral anomaly in 2 dimensions. So that was their goal. And they have other things in the paper which describe other relations in different dimensions. So this is an example of the Hilbert Hotel, where instead of going into the vacuum, the charge is moving off into the transverse direction, where the heavy modes, you do not have to excite a heavy mode. Everyone just has to move over one. So they don't have to go upstairs. They can just go sideways to the next room without cost of energy. Now, of course, when you go to a finite system, then you no longer have this infinite Hilbert Hotel. And if you push guests in on one side, they pop out on the other. And so when you go to a finite system, say periodic boundary conditions where the wall has to jump back and sign on the other side, you find that there is a right-handed mode sitting on the other wall, so that when you put in an electric field, charge is decreasing on one side, increasing on the other, and the charge is flowing through in between. Total charge is conserved. And yet chiral charge is not. And because of the regulator effects, no current is appearing on one side, and in fact, you can just cut it away. And instead of looking at a periodic boundary conditions, you can look at a slab. Now, this looked beautiful for a lattice construction. Why? Because chiral symmetry is explicitly broken in 3 dimensions. There is no chiral symmetry, and the fermions are very massive. So that suggests that, you know, if I added more mass to the fermion in the bulk, or took it away, or made the mass wiggle a bit, it wouldn't make any difference. So it looks robust. And so the question is then, can we just throw this on the lattice with Wilson fermions? So the idea then is look at the Wilson fermion on a lattice with a boundary. Very simple. At the time, of course, we didn't do the slab, we did the periodic boundary condition. So it looked like this would work. But when you look on the lattice, you find something sort of interesting, more complicated. So here's an example of the dispersion relation. Well, if I map out the energy, momentum versus energy on one of the surfaces of say the surface of a semi-infinite lattice, and I choose some particular value for m, and R, where M is the bulk mass term and R is the coefficient of the Wilson term, then you find a region in space, in this momentum space, where you get chiral fermions, and a region where you don't. Now, that had to be the case if it was going to work, because if this white region reached out to the corners of the Brillouin zone, you'd have doublers. But still, it looks extremely funny. How is this possible that you could have this weird discontinuity like that? And the answer is that if you look at the wave functions of the fermions on the domain wall, as you get closer to this edge, they're getting more and more extended in the extra dimension. And so what happens is that they delocalize at this point. And that is the discontinuity that occurs. So, so one way of thinking about it is that this Wilson term is a constant shift of a mass. It's a k-dependent constant shift of the mass. And so what happens is you have a step function and you get chiral modes. But if you shift the step function so all of a sudden both sides become positive or both sides become negative, then all of a sudden your chiral mode disappears. And so that's why you get a momentum dependent form for the wave functions of the chiral fermions, where you're talking about momentum along the surface. And when they reach a critical momentum, all of a sudden their wave functions get infinitely large, and you can think of them marrying the opposite chiral mode at the infinitely far away domain wall.
Excuse me, David.
Yeah.
I'm not sure I understand the figure. So there's a region of momentum space, you have a chiral fermions showing white region, and there are some region where you don't have a chiral fermions.
Right.
And what is left? Is that the circular region, or this shape has anything to do with some Fermi surface formed by chiral fermions? I don't quite understand what exactly is outside region with no chiral fermion actually meant. What it actually means.
What I mean is that I look for a solution of, so I can find the domain wall fermion by solving the Dirac equation, but it's not the Dirac equation anymore, it's the Dirac-Wilson equation with this extra term. And like Jakiv and Rebbe, if I look at zero momentum, I will find a localized mode on the wall. Now, that's if it has zero momentum. Now I try looking for boosted solutions, boosted along the extra dimension. And I find that as I go to higher and higher momentum along the wire, which is the edge, I find that the solution gets broader and broader, less and less localized. Until when I reach the critical edge here, my one particle solution becomes delocalized and there no longer is a normalizable solution for a zero mode on the wall. So this is not a many particle effect. This is a single particle effect looking at solving the Dirac equation for chiral modes at the surface. Does that make sense?
Okay, and just confirm again. So is the chiral symmetry here a non-on-site symmetry in this setup?
So it's, when you look at this free theory, no gauge fields, you find that the spectrum is actually looks like a solving for modes in a supersymmetric Hamiltonian. So you find a zero energy state which corresponds to the domain wall fermion, and then you find massive paired states where pairing is chirally paired in the bulk. What happens is at this critical value, you don't find a vacuum solution anymore. You only get the paired solutions in the bulk. So yeah, I don't know if I'm answering your question. You want to try one more time?
Well, certainly, there are some information pacing to me. I think I'm digesting. I think right now I get your point is that these are single particle picture that you're having fermions in K-space. Maybe you can keep going and say more consequence. I can probably understand better.
So is it fair to say that what happens at some larger momentum, the localized solution essentially disappears because you join the continuum, basically, the bulk continuum?
Right, there's no normalizable solution with a chiral, which is an eigenstated chirality.
I see. Okay. So, but is there a singularity in momentum space associated with this, or is it a smooth process essentially? So
the spectrum is not singular. You find that if you have a finite system, it's easier to understand. What happens is the modes on both walls extend until, and so you always have an exponentially small mass, exponential in the distance between the walls.
Right.
And then the modes start extending, and that exponentially small mass starts growing continuously, but then becomes order 1 at this boundary. So with a finite system, you do not have a infinite non-analytic point here, but an infinite volume limit you do.
I see. Okay.
So the system on the lattice actually ended up being much more complicated than we expected. So what I'm going to show here is a little movie where this arrow is going to run back and forth, where I change the ratio of the mass of the Wilson term from negative to bigger than 6. Okay, this is in a 3-dimensional lattice with 2-dimensional surface, 3 spacetime to 2 spacetime. Now, as I go around back and forth, I'm going to draw that picture that I just showed you. And in fact, when I start off with a negative m over r, there are no chiral mode solutions. So when I start varying this, though, this is what I get. So what I see is that if m over r is bigger than 6, again, no chiral fermions. But in between, if I stop this, I would find either one mode at the origin. Here's one mode at the origin, or 2 at these points in the Brillouin zone if I'm between 2 and 4. Or if I'm between 4 and 6, I only get one mode at this corner. And then if I'm bigger than 6, I get none. And furthermore, but the red and green means that the chirality is flipping. So it's one left-handed mode in this region of parameter space, 2 right-handed modes in that region, and one left-handed in this region, and then none. So this is sort of shocking. I didn't expect this. What's going on? And furthermore, well, let me first show you what the modes, if you look at a Hamiltonian, when I change m over r, this is what I see. So this is for an infinite system. So you can see that there's a period there where there's a mode that looks like a massless Dirac cone right there, but for other values of m over r, it goes away. And it goes away precisely at the point when the bulk modes, which are heavy most of the time, dip down and become gapless. So right at the point where that mode is disappearing, there are a whole bunch of modes in that vicinity. So this is not expected from the Callan-Harvey work. There's no analog in the Callan-Harvey paper. The number of chiral edge states changes discontinuously with the ratio of this parameter. And that causes sort of a conundrum, which is that we were able to explain the existence, in some sense, of the zero modes by the coefficient of the Chern-Simons term. So rather than saying the Chern-Simons term is there to explain where the charge goes, I could turn it around and say the coefficient of the Chern-Simons term tells me how many zero modes I need to have at the surface. So this must tell me that in the lattice theory, as I change m over r, the coefficient of the Chern-Simons term must change discontinuously. But this is strange because I had always thought of this coefficient as just being the result of performing a one-loop Feynman diagram. And I've never seen Feynman diagrams that change discontinuously with a parameter. So, and furthermore, this would be the analog of this diagram on the lattice where the propagators are a mess, the vertices are a mess, and I actually don't have a good hope of performing this calculation. Yet it has such simple behavior. So Martin Golterman asked me, how in the world could this work? It must be wrong. This couldn't possibly happen from a Feynman diagram. So we sat down and we thought about it along with Karl Janssen, and we came up with the following. Let's suppose we have some propagator, say a Dirac-Wilson propagator on the lattice. We know there's a ward identity that if the photons are minimally coupled, that the coefficient of the photon coupling to the propagator must be related to the derivative of the inverse propagator with respect to momentum. So now, if you say, I want to take this diagram, and I only want the Chern-Simons piece to it, you, first of all, have a trace of propagators and photon couplings, which is what you get from that diagram. And then you want the Chern-Simons term. So you want to pull out n powers of momentum, external momentum. So you differentiate with respect to n of these q's, and you set q to 0. I'm afraid it's hidden here behind the zoom thing. I'm going to set all the q's to 0 after I differentiate. And then I only want the part that's proportional to an epsilon tensor. So I'll contract with an epsilon tensor and put in the correct normalization. So here is the formula for the coefficient of the Chern-Simons term given this diagram. Now I use the ward identity and stick in that these photon vertex factors are given by derivatives of the propagator. I do some integration by parts. I perform my Taylor series expansion to momenta, q to 0. And in the end, I get this graph, I get this integral here. And this looks now very much like a topological winding number computation, because that's what you usually get, where S of p is some sort of map. So you take some sort of map, function of n plus 2n plus 1 variables, you contract it with the 2n plus 1 dimensional epsilon tensor. So now that was perfectly general. Let's take a look. The most general propagator you might expect is something that looks like a function of momentum times another vector function of momentum dotted in with gamma matrices. And so in particular, the Wilson-Dirac propagator takes that form, where I can pull out a normalization, which is n of p, and then it looks like some sort of unitary matrix, a cosine and a unit vector dotted in with all of the gamma matrices. So I can rewrite the inverse propagator, therefore, as a norm, which is p-dependent, times a unitary matrix. Now, provided that the norm is not 0, I can show that it factors out of this calculation. And in fact, the only thing that appears there is this V matrix. This V is a map from the Brillouin zone, which is a torus in 2n plus 1 dimensions, to this Dirac sphere, which is characterized by this theta vector. And you can show that the winding number, that this computes the winding number, which is an integer. This is correct whenever n of p is not 0. However, when n of p vanishes, then all bets are off. You lose all of the topology. When does n of p vanish? Well, it vanishes precisely when the bulk goes gapless. This is the propagator for the bulk fermion, and it goes to 0. That tells you that you've all of a sudden lost your gap in the bulk, and that's precisely when these domain wall modes can spread out and marry their chiral partner on their other wall and change their numbers. Furthermore, you can integrate through such a point and show that as m of r goes through the critical values, which is when m over r is a multiple of 2, is exactly when this vanishes, and you can integrate through them and see the jumps in the number of 0 modes as you go through them. So you can compute everything that we saw in that peculiar graph, where the number of modes changed and went through the Pascal numbers, I guess, the binomial numbers, and changed chirality each time. Just so in case people want to know what a map of a torus onto a sphere looks like, Mathematica kindly provides one where you can map a torus twice onto a sphere and visualize it. So that's winding number 2 map. So it turns out then that when you look at, so notice that these domain wall fermions really are nothing but ordinary Wilson fermions on a boundary. However, we're choosing an unusual value for m over r. So this is what the phase diagram for QCD with Wilson fermions is determined to be in 1996. Here we plot m over r mass over the Wilson term versus the gauge coupling. It turns out that there's a funny phase called the Aoki phase, which breaks parity, which is in here. And then you have these topological phases in the yellow region here, where these domain wall fermions exist. And the usual place you wanted to tune to was this point here at 0 coupling and 0 m over r. Of course, in a real simulation, you don't go to 0 coupling, but you tune to, because you're not exactly at the continuum, you typically have a cutoff in the order of 2 GeV inverse. So you're tuning to this point right here, looking for a phase transition here. So you're on the outside edge where there's a second order phase transition between the normal and Aoki phase. However, for the domain wall fermion instead, you sit in the topological phase here and you find the chiral modes living on the boundary. So the domain wall fermions are really a very small excursion away from the ordinary Wilson fermions. So this is very strongly connected to condensed matter physics, of course, namely through the integer quantum Hall effect. The integer quantum Hall effect is, in the Drude model, you expect a nice continuous way of continuous resistivity in the XY direction and in the XX direction, but what you see experimentally are these plateaus and these jumps instead. So the explanation that Laughlin gave in the early 1980s for this, he took the strip of quantum Hall material, and instead of applying a voltage across the end, he bent it around as an annulus and said, let's create the electric field going around the annulus by sticking a solenoid up through the hole in the middle. and I'll just ramp up the magnetic flux in the solenoid, and we know that that'll give me an electric field going around here. But he said, notice that when the flux inside that solenoid changes by 1 quantum unit, that then the gauge field outside the solenoid is only changed by a gauge transformation. And therefore, all the states have to return to themselves after you've increased by 1 flux unit. And so in a gauge where the Landau levels appear as rings in this annulus, what must happen is the electrons, as you ramp up the electric field, they must map onto pre-existing states. And what happens then is that these electrons just hop from ring to ring, or rather the rings grow continuously. And then as you go reach a gauge transformation, you end up with the same picture you started with. But the electrons, meanwhile, have been transported from ring to ring all the way out here until they reach the outside edge. And you get 1 electron per Landau level. Of course, in a real system, there's dirt, and that's part of the thing that makes the quantum Hall effect so interesting, is that the system, when it's impure, still shows this quantization, in fact, better. And so what's happening there is your Landau levels have localized states which are pinned down, and delocalized ones get depleted. And the theory still gives you the right picture. Because then what happens is, in the extreme limit that all of the bulk ones are pinned, is you still have, in this picture here, and you can see when I cut it on the edges, I still have sort of these half rings here, and they look like electrons hopping in one direction on one surface and the other direction on the other surface. And those are your chiral modes, and those 2 modes always persist, even if dirt pins down most of the bulk modes. And you go to the extreme limit where there's 1 mode on the inner surface, 1 on the outer, and as I turn on the electric field, it gets transported 1 electron at a time to the outside. But this caused Thales to get sort of perturbed, because in this picture here, you get 1 flux unit per lowest Landau level. But what happens when the Landau levels start getting split up due to dirt and become non-degenerate? So the argument, you might ask, well, does that mean that if I've got p levels here, I get p electrons per flux quantum? That didn't make sense. It didn't seem consistent with the argument. So the question is then, how does this work? So what you find out is that each level does contribute an integer number of electrons, but when you add them all up, it still adds up to 1 net electron. And he was able to show that with collaborators Komoto, Nightingale, and Denise, that it was a topological effect, and that the calculation actually involved a map from the Brillouin zone to the Bloch sphere. And so you can recognize that, and this is something I didn't understand until decades later, because I wasn't, or a decade later, because I was illiterate in the condensed matter literature, that this is in fact the same physics as the quantization of the Chern sinus term. Now, one of the very first models we looked at in '92 was what happens if you take a bulk fermion with 1 sign mass and charge 1, and a bulk fermion with the other sign mass and charge 1. In that case, you get the simplest anomaly-free situation on each wall, namely you get a Dirac fermion. So in this case, 1 fermion gives you a left-handed mode on one wall and right-handed on the other, and the other fermion gives you right-handed on the first wall and left-handed on the other. Now when I turn on fields, I have on each wall separately, I have this 1 + 1 dimensional system where I have a left and a right, and there's no net charge change on the wall on either side, but there is a chiral charge change, and that is what gets transmitted. So here's an example of a quantum Hall effect with no charge transmitted, but a U1 axial. And this is analogous to the condensed matter system called the spin quantum Hall effect, though the systems are somewhat different. The Wilson fermions are an example of what's called the Churn Insulator, and it has a U1 symmetry, not just T invariance. So this is similar, though, to the Kane-Meili effect that was discovered in the condensed matter system in the 2000s. Another place where there was overlap between what was going on in the condensed matter community and in particle physics, Majorana edge states. One of the theories that's interesting to look at on the lattice in high energy physics are supersymmetric theories. And the simplest one of those is the n = 1 supersymmetry, which just has a gauge field and a gaugino. The gaugino is either a Weyl or Majorana field, but it's massless, which is an adjoint under the gauge group. And the thing that's interesting about this theory, it's like so simple, because the only possible SUSY violating relevant operator you can write down would be a mass term for the gaugino. So if you want to simulate this on the lattice, all you have to do, you don't have to talk about creating a supersymmetric lattice there. All you have to do is forbid a mass term. So domain wall fermions were ideal for that. But the trick was, how do you make a Majorana fermion? So we constructed in the late 90s, we constructed an example of the Majorana edge state, and that was in fact used for Majorana, for simulating supersymmetric gauge theories in the mid-2000s. This had a parallel development at almost the same time, a little later, by Kitaev, who pointed out simple condensed matter system that had Majorana edge states. And they were very interesting. He realized that these would be very interesting for quantum computing, because when you take an electron and you split it up on two edges, then it's very difficult for any local noise in a quantum computer to disturb it, because it is such a delocalized state. And yet the source of noise that you expect would be local. So then a natural question is, there are other really cool things going on in condensed matter physics that didn't seem to have analogs in particle physics. So recently, just for fun, Sri Sen and I decided to see, is it possible to see the fractional quantum Hall effect in a relativistic quantum field theory? So the condensed matter physics is pretty complicated in the UV. The question is, but we don't want to reproduce that, but it does have a very simple low energy effective theory in the IR. Namely, you can describe it as two different gauge fields, U1 gauge fields, with a Chern-Simons term that mixes the two. So you've got a Chern-Simons term just for the little a field called the statistical gauge field, but you also have one that mixes it with the photon, where m is an integer, quantized as we've come to expect the Chern-Simons term to be quantized, namely with an integer coefficient with the proper normalization. But now if you look at the equation of motion, or equivalently integrate out the little a field, it gives you that little a is big A over m. And so when you substitute that back in, you get a Chern-Simons term for the photon field with a fractional coefficient. So the question then is, can we reproduce this effective theory that the condensed matter physicists painstakingly deduced with a relativistic system? And the answer, with only integer charged particles, the answer is it's extremely simple. So here's an example. We'll have a U1 cos U1 gauge theory. I'll call the bosons A and Z with two different couplings, and introduce three different types of fermions. One's charged only with the photon, one's charged only under the Z, and one has charge under both. And they've got a certain number of flavors of each. And it's convenient to adopt the convention that the sign of n need not be positive, but signifies the sign of the bulk mass term. So if n psi is 3, it means I have 3 flavors with a positive mass, and if it's -3, it means I have 3 flavors with a negative mass. And you can put in polyvelars and so on to regulate the theory. Well, when you integrate out the fermions, you're left with a theory of only photons, and you find, sure enough, you can compute that the filling fraction, this factor nu here, is not an integer. It's given by this formula here, where these were the flavor numbers of the fermions that you put in. And what's happening here then is that you've integrated out the Z, and there are these mixing terms that the fermions induce mixing terms through Chern-Simons operators, and allowed you to get this funny term in the end. And you can compute this analytically. So then what about the edge states? That's a little bit confusing, because when I solve the Dirac equation, and this is not on the lattice, the continuum, I get integer charged, I get fermions on the edges with integer charges under both U1s. So how in the world does this work then with anomalies? Well, it turns out that when you want to ask what is the coupling of the photon to these edge states, it's true that the photon couples directly with an integer charge, but it also couples through the z through these diagrams here. So when I integrate out the z, I also induce new couplings of the photon to the edge states. And when you compute them, you find that the charges of the fermions stuck to the domain walls have these funny fractional forms. And you can then take these fractional charges and check that, in fact, anomalies cancel correctly, that the bulk currents exactly account for the anomaly, the U1 anomalies along the edge. So just for fun, you can construct models with the following flavor numbers, and you find the following filling fractions. There are no especially exotic or funny ones. It's easy to get just about any fractional filling fraction you want. And these are the charges of the edge states in these particular examples. Another thing you can do if you want is construct a theory where each wall, just like we did with the Dirac fermion that gave the quantum spin Hall effect, make each wall itself individually have anomaly cancellation for the gauge charges. That's not necessary because if it has an anomaly, the charge is conserved by going across the other wall. But if you choose the right quantum numbers, then each representation on each wall separately is gauge invariant anomaly free. In that case, there can be no charge current flowing through the bulk. So the question is, can we come up with an example where we have non-charge flavor numbers going across, but are fractionalized? And sure enough, it's very easy to construct a model like that, where the filling fraction is 0. There is no photon Hall current. But if you look at, say, a flavor current, say chi1 number, you calculate its transverse conductivity, and you find it's fractionalized. So the question I have is, does this sort of fractional quantum spin Hall effect have condensed matter analog? Unfortunately, it's a lot easier to play games on paper in a high energy physics theory than in a material system, but it might be interesting to look and see whether condensed matter systems can be constructed where you get fractional non-charged quantum numbers being transferred between surfaces.
David, I have a quick question, please.
Yeah.
Go back to the fractional state that you presented before. In the condensed matter setting, the fractional Hall effect appears due to the fact that in a Landau level, the interactions are always essentially infinitely strong because they are much bigger than the vanishing kinetic energy. And so it's essentially a strong coupling effect, whereas this theory appears to be a free field. Is that fair to say that?
So I'd say that these high energy physics theories are sort of like Churn Insulators. The time reversal violation does not occur due to any B field, but because of the mass in the bulk.
Yeah.
So I don't know what the analog of Landau levels is in this theory.
But you don't need any strong coupling physics for this.
I'm sorry?
There is no strong coupling physics associated.
No, it's all perturbative. It's easy to compute everything.
So it's all in the weak coupling regime, essentially.
Yeah, that was one of the attraction of this sort of model, is that the strongly coupled complicated UV physics in the condensed matter system wasn't necessary for getting the effective theory with the Chern sign terms. And so that was one of the attractions of looking at a model like this, I thought.
Okay, thank you.
Right.
Can I ask a quick question?
Yeah.
Sure. So does this have you looked at any other symmetries other than time reversal, like reflection, or does it have any anti-unitary symmetries at all? Or like the product of reflection?
It probably does. I don't, there are various flavor symmetries that would be anomaly free. I can't enumerate them at the moment. Sorry.
Okay.
I also forgot to put in the reference here. This is a paper that was, I think, yeah, this is a paper that it was published recently in PhysRevLet by myself and Srisem.
Okay.
So a related question to what I asked before, do you have anyons in that theory?
Yes, well, no. Well, okay. So I can put in scalar fields in the theory and get anyons and get all sorts of weird fractional statistics. But I have to put them in as extra degrees of freedom in the UV. I cannot, so just like I am putting in the statistical gauge field as a fundamental field in the UV. That's how I get away from strong coupling. Likewise, I can put in scalar fields and find all sorts of weird fractionalized anyons in the IR, but I do not see them arising dynamically, I don't think. It didn't seem to exist there on its own.
Okay, thank you.
That's the price of going away from strong coupling, is that you have to put in what you want to get out.
Yes, of course.
So we've seen some interesting analogs here. The QCD domain wall fermions is analogous to the integer quantum Hall effect, including, and one realizes after the fact that when Wilson wrote down his theory, it's got interesting topology in it. You can write down models with the gauge anomaly cancellation at each wall, and the analog there is the quantum spin Hall effect. You can look at supersymmetric n=1 domain wall fermions, and that is analogous to the condensed matter systems with Majorana edge states. And then for fun, as I said, showed that you could also reproduce the fractional quantum Hall effect, and including something sort of bizarre, which is a fractional spin quantum Hall effect.
Excuse me, naive question. In condensed matter, quantum spin Hall effect usually has some U1 symmetry, also a time reversal symmetry. I think it's related to a previous question. Are there time reversal in your model?
So time reversal symmetry does not play a big role in these models. With the case where you get a Dirac fermion on the edges, so it looks analogous to the spin quantum Hall effect. If the bulk fermions have equal and opposite sign mass, then you do have a time reversal symmetry. But you also have U1 symmetries, and so you find that the time reversal symmetry is not needed for the low energy physics. I have not thought about whether you could have a theory, high energy theory with no U1 and just time reversal symmetry. That's not a direction I've looked.
Thank you.
Yeah. So, question is not so much. Oh, one thing that's sort of funny is that when I first thought about the domain wall fermions, it was 1988, and I marketed it around to QCD people and asked, so how would you like to simulate QCD with good chiral symmetry? And they said, extra dimension, forget it. That's too hard. We'll tune Wilson fermions. So I stuck it in my drawer for 4 years and published it in '92. But the reason for that is well understood, because 1988 was the year I bought a 40 megabyte external hard drive for $700. So adding an extra dimension was no small task for somebody who wanted to simulate QCD. So it's understandable. Now, what's the direction to go for the future? Where are interesting areas for cross-fertilization? So two of them I singled out here. One is the overlap operator, which is technology that's been developed in the high energy physics lattice community, which I think is pretty cool and seems not to have been noticed by the condensed matter community. And then the other thing is a question which has been of great interest for many years in the high energy community, which is how do you come up with a non-perturbative regulator for chiral gauge theories? And that has been attracting lots of attention lately in both high energy and condensed matter communities. So first, the overlap operator. So Neuberger and Narayanan asked, well, in a domain wall theory with an infinite separation between walls, what happens if I integrate out the bulk modes and write down the effective theory that is only a theory of these two edge states, assuming a gauge field which is constant in the extra dimension? So in other words, this is not trying to describe a chiral gauge theory, it's trying to describe a vector-like gauge theory with a good chiral symmetry. So the idea is you integrate all the heavy bulk modes and write down the effective theory of the gauge field and the edge states. When you do that, you're going to get some sort of Dirac operator, which acts in this lower dimensional space of the edges. Well, they were able to do that explicitly by doing a transfer matrix of the domain wall fermion on the lattice. And they found that D was the limit of the following object, where T is the transfer matrix in this transverse direction. They're in Euclidean spacetime, and the way they thought of this is by saying, well, what happens if we consider the extra dimension as time? Since in Euclidean spacetime, it doesn't matter what direction it is time. And they asked, how does this thing evolve? And they started thinking about transfer matrices. And they were able to compute this analytically in the limit that the wall goes to infinity, and they came up with this incredibly simple and beautiful answer. The D is just the unit operator plus gamma 5 times a sine function of the 5-dimensional Wilson Hamiltonian. This is a very beautiful result because it's got 3 different operators whose eigenvalues are just plus or minus 1. And yet all the dynamics is in how they align with each other. And the claim is that this correctly reproduces Dirac fermions as a function of the gauge field, which is embedded in that Hamiltonian. So what this operator does, this is say the continuum eigenvalues of D slash, they're paired plus minus and they're imaginary. Imaginary in Euclidean spacetime. So here would be the eigenvalues in the continuum. And what the eigenvalues of this operator do is they live on a circle, because you can show that this is 1 plus a unitary operator. And so they live on a circle here where the eigenvalues that you want for the continuum are all mapped into this little space here. And so when you take the continuum limit, it's only the eigenvalues near this point here that are interesting, and they reproduce the Dirac operator's eigenvalues. And it's very simple to show that with this operator. Furthermore, you can show explicitly and analytically that D obeys the Ginzburg-Wilson equation. So they found the solution. So that explained, now we've come full circle here. We've said we created these chiral modes with the domain wall fermions. They are beautifully chiral. It's obvious that there's no multiplicative mass renormalization because there's no overlap of their wave functions in the extra dimension. So there's no way you can write down an operator that involves both of them that doesn't vanish. And yet the anomaly is reproduced. So chiral symmetry is not exact. And the anomaly is the only way chiral symmetry is violated. So how is that possible? Well, this operator explains it. This is the effective theory. It obeys the Ginzburg-Wilson equation. Furthermore, you can use this operator and analytically show how you get the correct anomalies out. So the question is, could this be useful for condensed matter system for describing the dynamics of edge states? It seems like too often people assume the edge states can be sort of just reproduced by a continuum theory, but the question is, on the lattice, can you understand them? And the answer is, this is the way to do it. Because if you try to write them down as a simple lattice theory of ordinary fermions, you'll get doublers, or you'll get some other problem with the Nielsen-Anemia theorem. So I leave that as an open question. It seems to me that it's unknown technology in the condensed matter system. Now let's switch finally to my, the last topic I'm going to discuss is chiral gauge theories. Chiral gauge theories, in 4 dimensions, you can always write any gauge theory with the fermions all as left-handed Weyl fermions. So a chiral representation is one where the gauge representation of these left-handed chiral fermions is complex. That means you cannot write down a mass term, because a mass term in terms of Weyl fermions, you just take 2 left-handed Weyl fermions and you contract them with an epsilon tensor. And if it's a complex representation, you will not be able to make a gauge singlet by doing that. Now, no, I don't want to get people angry with me. There's been no proven non-perturbative regulator, I'd say. No one's been able to show and actually do a computation with the chiral gauge theory and show that it makes sense. But the thing that's sort of astonishing is there's also no perturbative one. There's a rule of thumb that people use to say that when you use dimensional regularization, you take gamma 5 to anti-commute with the gamma matrices when they have indices less than 4 and commute with indices greater than 4. And that's shown to reproduce the anomaly correctly, and it's shown to work up to 2 loops. But as far as I can tell, asking people who do higher order calculations, no one's proven that this works beyond second order, beyond 2 loops. Now, why would you be interested in understanding a non-perturbative regulator for chiral gauge theories? It used to be that people were very interested in strongly coupled chiral gauge theories because these theories are known occasionally to have massless composite fermions and all sorts of other very peculiar phenomena. And so it's always interesting to ask whether the fermions we know and love are fundamental or whether they're composite. And so compositeness might explain the family number, for example, or something like that. The problem is, of course, is that with the LHC, we've pushed off new physics to some higher energy scales, shorter distance, and higher budget than we currently have. And so the only chiral gauge theory we know at the moment is the standard model. Now that's a big a big Karl gauge theory. It's the one that describes the world. It is disturbing that we do not have a known regulator that, that works all orders. But in terms of practical consequences, everybody's happy with perturbation theory in the standard model. There's no strong interactions that until you get to low energy, where the theory is well described by a vector-like theory. So some of the motivations for understanding the theory have gone away, Karl gauge theories. But one hope that I would have is that if you do find a non-perturbative Karl regulator, there might be some fingerprint left over that would give us actually new predictions for the standard model that we do not expect. So what is a Karl gauge theory? Well, if you look at a path integral and at some level, yes?
Can I clarify the language? So when you say a regulator, can this just be regarded as some kind of a lattice regularization? I think somehow I don't understand the regulator you mean. Maybe you want to rewrite some propagator in terms of lattice form, but can I just provide you a lattice regularization of the Karl gauge theory?
Sorry, what does?
The question is that what do you mean by the regulator here?
Okay, what I want is a completely finite system that has a gauge symmetry with a Karl representation.
Okay, great.
In the low energy.
I agree. So doesn't need to write some maybe propagator look like a Ginzburg-Wilson or Nuremberg, that type.
Well, no one knows how to do it with Ginzburg-Wilson fermions. Okay, so I mean, sorry. So Lucier has shown that a Ginzburg-Wilson operator or overlap operator could be used in principle to formulate a U1 axial, a chiral U1 theory. Okay, that's been shown in principle, but it's not a practical, at least to date, it's not been a practical construction that could be used for simulations. Kikukawa has extended that and claims that he can do that for non-abelian gauge theories too, using overlap operators. So when I say no proven non-perturbative regulator, for me, a proof is going to be when somebody can do a numerical simulation and show that you actually get a sensible result in the continuum. So we know that if you have a left-handed Karl fermion and a right-handed one, you get a Dirac fermion. You can show that the Karl fermion determinant for a Karl gauge theory is, in some sense, the square root of the Dirac operator. If I have a representation R and R star, then it's square for the chiral modes and its mirrors together would give me the Dirac operator. So in some sense, I want the square root of the Dirac operator, but of course, how do I take the square root? So let me just show some naive things. So let's plot eigenvalues of the Dirac operator versus gauge field in some path in gauge field space. It's some reference field. You've got some reflection symmetric imaginary spectrum for the eigenvalues. And as you change the gauge field, they flow somehow. And because of the gamma 5 symmetry, they're always paired, plus and minus. Now, you could say what I'm going to, and these eigenvalues are gauge invariant. So you might say a good gauge invariant regulator would be just take the positive eigenvalues and multiply them together. Or you might say, let's just take all the positive one at some reference scale and then track them continuously as I change the gauge field and multiply those. So I'll get sign changes. The problem is, well, this one's obviously non-analytic at some gauge field. And I argue that you don't want things that are non-analytic because then currents and everything become infinite. This one looks well-defined and gauge invariant, but it's not going to be local. There's no way to define this so that you get this from a local fermion action. So these are just two examples of gauge invariant square roots that don't work. So in general, you can say that the determinant for a Karl fermion is its modulus times the phase. The modulus will be the obvious positive square root for the Dirac operator, or any square root you want. The question is then, what is the phase? And so Luis Alvarez Gomez and the two Della Pietra twins at Harvard in 1986 were able to show that if you take the phase relative from one gauge field relative to a reference gauge field, that it was given by something called the eta invariant of a Hamiltonian, where the eta invariant is just the regulated sum of signs of eigenvalues. And the operator that they call H is an operator where you go to an extra dimension and you introduce the gamma 5 and a new dimension t, the fifth dimension t, and look at the evolution of the eigenvalues as a function of t, where t is your parametric, your parameter along the path in gauge field space. So A of t interpolates from your reference gauge field originally to your final gauge field. And as you change the gauge field, the eigenvalues flow, and the eta invariant is the measure of the signs of the eigenvalues of this 5-dimensional Hamiltonian. So the eta invariant just basically traces the sign of H. This looks awful lot like the overlap fermion. It's very suggestive, but I don't feel like there's been a really tight connection made yet on this. Furthermore, you do get, in a theory where you have anomalies, you get an additional contribution which comes from the Chern-Simons operator in this 5-dimensional space. So once again, when you talk about chirality, you're almost always, it seems, directed to an extra dimension. So the domain wall fermions and overlap operators, again, look sort of natural. But the problem with this very beautiful formulation is that you still need a numerical method. If you need a regulated non-perturbative method for computing this eta invariant. So the problem is when you put fermions on the lattice, you almost always basically start off with Dirac fermions. The question is, how do you get rid of mirror fermions, right-handed mirror fermions? You want to keep the left-handed ones. And how does the theory know that it should only allow anomaly-free theories and that your method's going to fail if it tries to give you, if the target theory would be anomalous? So 3 ways come to mind. One is destroy the mirror fermion by destroying gauge symmetry. Throw in a mass term, which we said will violate mass, gauge symmetry for the mirrors, and then try to restore gauge symmetry in the continuum limit on the lattice. So that's one way. Another way is take the mirror fermions and hide them. Keep them here, but somehow make them invisible to us without making them heavy. And then a third way is make the mirror fermions heavy and decouple. So there may be other methods, but these are the 3 possibilities that seem to be the possibilities to me. So first one, decouple the mirrors by breaking the gauge symmetry, give them a direct mass. This is the subject of a paper by Goldman and Shamir. It's nice work. It's been shown to work in perturbation theory, so you gauge fix, you give mass the mirrors, you tune to the continuum. It's been worked out in perturbation theory. It's nice, but it's sort of not practical, really, for non-perturbative computations, because you don't know what you're supposed to be tuning toward, and there are many, many operators to tune. And it doesn't give you very deep insights into chiral gauge theories. One thing I want to stress is the type of tuning is not just tuning to get the right particles massless, but if you break gauge symmetry, it's possible to write down an operator in 4 dimensions, which looks like, if A is your gauge field, A1, A2, A3, A4 at a site is invariant under the hypercubic symmetry, even though it's not invariant under the Lorentz symmetry, and it's a marginal operator. So if you break gauge symmetry and you've got a 4 vector on your lattice, you're not just going to get weird spectrum and things like that. You're going to get a non-Lorentz invariant theory. Hiding mirror fermions. So this is the subject of a couple papers I wrote with Dorota Grabowska, not M. Grabowska, I'm sorry. I don't know how that got there. Okay, so this was sort of for fun. It's not a theory I especially want to push, but it's sort of interesting. So the idea was to use domain wall fermions. The idea was one of the ingredients we were looking for is we wanted to understand how hiding them would fail if the target theory was anomalous. That seemed to be an important ingredient. The domain wall and the Chern-Simons term will help us understand that. And we also wanted to make a connection with the earlier work by Alvarez-Gomez et al. So the idea was you start off with a compact space with a left-handed fermion on one side, one wall, and a right-handed on the other. We make each side individually anomaly-free, so there's no charged Chern-Simons current in the bulk. And then, I already mentioned that, but we still have mirror fermions, so you want to get rid of them. So the question is, how do I do it? So one way you might think is, let's just cut the space and cut them out. But no, right-handed fermions will appear at the new boundary. Well, maybe you could just put the gauge fields localized around one wall. And the problem is that, well, this extra dimension, sort of like you can think, if you think about it as flavor, you can't have one flavor coupled to, which is gauge, coupled to one that's not through a hopping term, because that violates gauge symmetry. So you have to put Higgs fields along this region here. And what you find is that by breaking this extra translational invariance in the extra dimension, you destroy the symmetry that gave rise to the separation of domain wall modes, and you end up either breaking gauge symmetry or finding new modes appear on this boundary. So instead, we decided to do something called gradient flow. The idea is to not have the gauge field be continuous all the way around the extra dimension, but have it be related in the extra dimension to a gradient flow similar to what was used by to prove theorems in gravity about singularities. You take whatever gauge field is on the wall where you're interested, and you evolve it in the extra dimension using the classical Euclidean equations of motion, which has the effect of acting like a heat equation, and it smears out the gauge field so that the fermions on the far wall just see the smeared out gauge field. This is a sort of strange thing to do, but it preserves gauge invariance. So what you find is that the effect is that the fermions on the far wall look like they've got infinitely soft form factors. And so they're there, they're all around us, but we can't probe them because when we bounce something off them, they're vanishing, they have vanishing form factor. Furthermore, you can show that the theory only has a local 4D effective theory when there's no charge Chern sinus current in the bulk. And that is exactly the anomaly cancellation requirement. So this is a feature. This has features I don't like at all. It violates cluster decomposition and might likely give a non-local theory that's sick in the continuum. But it has a feature that I like, which was there was a one-to-one correspondence between the theory failing and there being gauge anomalies, even on the lattice. And that I thought was an important thing that's missing in many formulations. So I'm not pushing this. It violates cluster decomposition. It could give rise to non-local instanton effects, which if they were small would be really cool, but I have no proof of that. And it's sort of baroque and it's possibly dangerous, even if it's fun. So let's go on to the third one, which is gapping the mirror fermions without breaking gauge symmetry. So this is an idea put forth by Eichner and Preskel in '86. They proposed putting in strong 4 fermion operators on the lattice to gap mirror fermions without a bilinear, which would break the gauge symmetry. So, and a key thing has to be that if you're going to follow this procedure, you've got to understand why an anomaly-free vector theory can't turn into an anomalous chiral theory. In other words, why you have to understand why the specific choice for fermion representations in the vector theory is critical to make this thing work. So first thing, some motivation from the continuum. I think the earliest example of gapping chiral fermions without breaking chiral symmetry was given by this paper by Howard Georgi in 1979, where he considered, for completely different reasons, a strongly coupled SU5 gauge theory. So what Georgi was interested in was the question whether there could be massless composite fermions. And this theory with a 5 bar, a 10, and a singlet, you don't need the singlet for the massless composite fermions, arguably does. And the point is that this theory also has a global anomaly-free chiral U1, where this zeta particle carries 1, psi, which is the 5, carries charge -3, and chi, which is the SU5-10, carries charge 1. These charges are chosen so that there's no U1 cubed anomaly, there's no U1 SU5 squared anomaly. Now, Georgia gave strong arguments for why this theory confining would give you a massless fermion. So the first step is you need to match anomalies. That's a Tufts great contribution, that any theory gives composite fermions in the IR has to satisfy an anomaly matching condition where the anomalies agree in the full theory the UV theory and the IR theory, because otherwise you could get an inconsistent picture where if I gauged it, the theory would make sense in the UV and would not make sense in the IR. So he showed that there is a composite particle, psi-psi-chi, which is gauge invariant. And so if the theory confines, you could get this as a state in your spectrum. Furthermore, it carries, it's a singlet under SU5, but it carries the correct charge of -5 to agree with the anomaly contribution of from the, oh, sorry, this zeta should have charged -5. It has the correct charge to explain the anomaly cancellation. Sorry, the zeta should have charged +5 or something like that. The opposite of theta.
Yes, excuse me.
Sorry about that. However, the reason why they gave why the argument was strong is because you could argue it two ways. You could argue it either through confinement and anomaly matching, or you could say that you have most attractive channel. These fermions condense into bilinears. They Higgs the gauge field down to SU4. All the stuff that's vector-like under SU4 gets massive, and you're left what's neutral under SU4, and it gives you the exact same spectrum in the IR. So what he didn't do, what you can do then, is you can take the singlet, you can couple it to this theta particle through a 4-fermion interaction, and now this irrelevant operator would lift the massless composite fermion, give it a mass, and show that you can do it without violating the U1, except for it's not obvious given the U1 charges I erroneously wrote down. But yes, this would be invariant under the chiral U1, and yet, so you do not break the chiral U1, but you gap the chiral fermions.
Excuse me.
Yes.
Sorry, I asked several times. Just confirm. The U1 here actually relate to the baryon minus lepton number up to some hypercharge, right? It's a B minus L and up to some.
It's the B minus L U1 from the SO10. If you embedded this as a 16.
Yes. So as you clarify, just make sure the zeta, that label for the one of the singlet on the SU5, that one actually has a charge 5, I think, right? Under the U1 B minus L. Actually, it's 5 times B minus L minus 4Y hypercharge. I think you make that clarification. I think I just double check with you, and I agree with you what you say.
Okay, good.
Yeah. Okay.
So another interesting paper just appeared a couple of months ago by Razamat and Tong, where they say they got interested in this question, but they're not interested in the lattice UV regularization. They're interested in theories where the IR gaps chiral fermions without chiral symmetry breaking. And they gave a number of examples where they used a lot of the technology from supersymmetric gauge theories that was developed in the 90s to argue that you've got a large class of theories where you can do this. However, for a lattice regularization, you have to start with a fully vector-like theory. They start with a chiral theory and just show you can gap them. In the lattice theory, you want to start with the fully vector-like theory, and you need strong irrelevant operators at the cutoff to gap the mirrors. So this is dangerous business. Once you have operators which are naively irrelevant that become strong, then all bets are off on what the dimension of any operator is, and you have a very hard time knowing what is relevant and what's not. Once that happens, you have to ask, well, how do you search the parameter space? If you have a second order phase transition to a symmetric gapped phase, will the resultant continuum theory even be, will it be gauge invariant? Will it be, I didn't mean gauge invariant, I meant Lorentz invariant. So will it be a Lorentz invariant? You don't know, because you're talking about short distance physics where at the lattice. And finally, just a sociological comment that at least in the lattice gauge theory community, no one will believe a solution until you see some full simulation, because there have been lots of examples of models which seemed like they were going to work using mean field arguments that then ended up failing. However, there's an interesting example that has spawned a lot of work, which in this 1+1 dimensional model by Fitkowski and Kitaev, where they showed that they gave convincing arguments that you could put in interactions on a 1+1 dimensional model, which could gap and yet not break chiral symmetry. So the interaction that they looked at was examined by Chandrasekaran and Akyar, as well as by Karl and collaborators. They took the same interaction as Fitkowski and Kitaev, but they went to 3 space-time dimensions and 4 space-time dimensions and looked for symmetric gapped phases, and they found them. So in particular, here's from the 4-dimensional simulation from a 2018 paper by Karl and Sheikh. And they originally, so what is the theory? Oh dear. It's hiding under my Zoom window. I don't know if I can change that. So what happens here is you've got a fermion bilinear sigma. You've got 2 of them, and in between you've got the inverse of an operator. Let me leave full screen mode for a moment so you can see it.
I think we can see it perfectly well, actually.
I'm sorry?
We can see it perfectly well, I think.
You could see it. Okay, I'm sorry. I can't see it. It's hiding behind it. So I'll go back to full screen. Okay, so you've got the inverse propagator of a massive scalar. So there's a mass term for the scalar, which if it was just that, it would be an auxiliary scalar that when you integrate it out, gives you a contact for fermion interaction. But they also have a kinetic term for the scalar, so kappa. So there are 2 parameters that they play with, and they look at the IR theory. One is kappa, the kinetic term for the scalar, and the other is g squared, which is the coupling. So you get a 4 fermion interaction with strength g squared, but it's got some spatial dependence, which is determined by kappa. And psi is just a fermion bilinear. So first of all, they looked at it with kappa equals 0. That's along this line here. And they found 3 phases. There's the weakly paramagnetic phase, strongly paramagnetic phase, and antiparamagnetic phase. And this phase here is symmetric and gapped. This phase is massless and symmetric, not gapped. And you'd like to find a second order phase transition between the 2 to define a continuum theory. However, they found a broken phase between them. You could not connect the 2 with this. You could not find a second order phase transition that connected these 2. However, when they turn on kappa, then they find that they can. There seems to be a region in here that is not characterized by any order parameter where the correlation links get long. So they are hypothesizing that this might be the correct place to look for a gapped symmetric continuum theory, although they have not shown that such a thing would be Lorentz invariant. So that's another thing that has to be checked. But at least that's encouraging that there do seem to be such theories. And that was a numerical simulation. And part of the thing I should mention is that when you're looking at theories where, chiral theories, we've already talked about how you expect the fermion determinant to have a phase. And so generically, these theories will have sign problems when you try to simulate them using Monte Carlo methods. So it's really a tour de force that work by Chandrasekaran and collaborator and Karl collaborators were able to find a way of actually doing real numerical simulations and showing that these exist. So domain wall fermions or overlap fermions. For the latter, there's some interesting papers by Kikukawa and Lushern. Are natural places to construct chiral gauge series, especially the Eichten-Preskel type, because you're starting off with good chiral symmetry and you're geometrically isolating the mirrors from the ordinary fermions. So it's easier to picture putting an interaction that affects one and doesn't affect the other. It may not be necessary. The example given with the staggered fermions is a counterexample where you do not have domain wall fermions. There have been a lot of condensed matter papers on this, spurred on by the work by Kitaev et al. They have gotten more mathematical than I can follow. I apologize. The thing that the condensed matter physicists have brought insight on are the role of discrete anomalies, which play a critical role in understanding how to gap these chiral fermions, which is a discussion that was not in the high energy literature at all until the condensed matter physicists brought it in. So that's a real big advance, I think. And I am not going to comment more about these papers at the time, but I encourage people to look at them. So open questions. Can Lorentz invariant symmetric gap phases be found in full simulations with these models? And a question which I am disturbed by is that the way people tend to proceed is to make sure that they break all the appropriate anomalies so that you could not have a target theory which is anomalous, and then hope that it has the right phase and the right phase transition to get long correlation lengths. But I find it sort of disturbing that there's no insight into how, if you start off with a theory that would have been anomalous in the continuum, how does that affect the dynamics? How does that change the phase structure? Because anomalies seem like a very subtle effect that don't affect the way fermions condense. My worry is that the theories with and without anomalies will choose the same route, namely they'll cause bilinear condensates, or they'll break Lorentz symmetry or something. They'll find the easy way out to avoid having a continuum four-dimensional anomalous theory, rather than a sneaky way that allows four-dimensional anomaly-free chiral gauge theories. So far, I haven't seen a good argument for how, if I introduce a fermion that introduces an anomaly, how that screws up the dynamics. A really interesting question to me is whether are all anomaly-free chiral gauge theories that you can imagine obtainable, or is there only a special class? So, for example, can you show that the only anomaly-free gapped chiral gauge theories you can get on lattice are subgroups of SON? SON not having any anomalies is a particularly attractive possibility, but that would have dramatic consequences if you wanted to talk about what possible grand unified theories could exist. And finally, I don't have strong hope for this, but it would be the most wonderful thing, of course, would be if any of these regularizations left behind an observable fingerprint in the IR that might be seen in experiment. So let me conclude. Relativistic quantum field theory can be formulated on a lattice. It can exhibit all sorts of rich phenomena that are seen in condensed matter systems. Explorations into regulating chiral symmetries led to many discoveries that on the high energy side that parallel roughly concurrent, earlier in some cases later, and other discoveries in the condensed matter physics, integer quantum Hall effect, Churn Insulators, Topological Insulators, quantum spin Hall effect, Majorana edge states, and so on. And one can construct even more examples of exotic stuff. And a well understood lattice theory for chiral gauge theories, though, still, in my opinion, does not exist. But the insights from topological materials and condensed matter physics seems key. And there seems to be a lot of activity and a lot of progress. And it's especially interesting is the role of these discrete anomalies. And so I expect a lot of interesting cross-fertilization in the future. Thank you.
Thanks, David, for the wonderful talk. Any questions from the audience?
Yeah, can I have a quick comment? I just want to say that in condensed matter literature, the quantum spin Hall effect and the spin quantum Hall effect actually means very different things. So actually, yeah, right. Yeah, it's better not to mix these two phrases, if possible.
I'm sorry, say it again.
Yeah, I'm just saying that seems like in your talk you use the word quantum spin Hall and the spin quantum Hall interchangeably. I mean, we know what it means, but actually in condensed matter community, actually these two basically mean very different things. So actually,
okay. Yeah, I apologize. I find something.
It's kind of confusing. I'm just saying, yeah, right.
Yeah, I have found that some of the nomenclature in condensed matter physics to be confusing because there are meanings that are not encoded in the words, but in the word order.
Yeah, right.
Yeah, I apologize. That's part of the ignorance between the communities understanding that. What I was trying to refer to was just the transmission of non-gauge quantum numbers through the bulk.
Yeah, I get that. Yeah.
Any other questions or comments?
Can I ask a question, Juven?
Yeah.
Hi, David. How are you doing? Thanks for the talk. I really enjoyed it. I have one question and one comment. The question is the obvious way to couple gauge fields to fermions that live just on one wall and not the other, which I think is the way you suggested in your original paper, suffers from this issue that Golterman and Shamir subsequently pointed out about the fermions living on the boundaries of the waveguides. And so ultimately it's not a chiral theory. That analysis was not done for the most general possible theory on the lattice. For example, it didn't include 5D gauge fields, it only had 4D gauge fields. The boundary of the waveguide was taken to be just one lattice spacing big, which introduces UV physics. And yet it doesn't appear that many people have studied the possibility, and a very important possibility, that by generalizing this, one could evade these waveguide doublers. you have any comments on this?
It has not been completely explored. A historical note, actually, the first thing that was suggested was having space, having the gauge couplings be space dependent in the extra dimension.
Right. Yeah.
So the idea was to go from like a confining phase to a Coulomb phase or something like that. That got stalled by people who simulated 5-dimensional gauge theories found with this extra spatial dimension. They found evidence for layered phases and non-continuum limit first order phase transitions. This certainly was not exhaustively studied. It was last looked at in the early 1990s with rather primitive computing resources and certainly very primitive theoretical resources. So that is another direction one might look at, whether the spatial dependence of the gauge coupling could be important, or as you say, whether the waveguide model could have more sophisticated forms. But yeah, without some sort of idea to lead you into the many-dimensional parameter space where you want to go, it's not very attractive unless you have some idea why something might work. At least that's my opinion.
I see. The comment is slightly different. You mentioned that anything that tries to gap just the mirror fermions has to have a failure mechanism. They can't possibly gap something preserving a symmetry which is anomalous. And I'm not worried about that. You seem to think that this was a big issue, but if you can write down interactions which gap a bunch of chiral fermions, they're only possibly going to work if those fermions have no anomalous symmetry. And so the models we studied in the continuum, that's exactly what we found. If there was no anomalous symmetry, we typically could find ways to gap them. And if there was an anomalous symmetry, we couldn't. And of course, it had to be that way by anomaly matching. So somehow I don't see that as an issue. One could only ever gap things that don't have an anomaly.
If I may add to that.
Eric, please.
Hi, if I may add to that, actually, that's exactly right. I'm with David. We actually studied on the lattice a theory that tried to gap anomalous representation, and the mirrors just remained massless. That was it. That's how the anomaly was matched on the lattice.
Yeah, I have always favored a geometric picture. I'd like the waveguide picture because I know that in anomaly-free theory, there are no currents going through that area, and if it's anomalous, there are, and I can see how that might change the dynamics of what goes on the boundary there. And so I would be much happier with, I mean, aesthetically, it seems like it makes more sense to me that a solution would be clearly sensitive to the anomaly, and you'd be able to easily see it rather than saying, obviously, the phase I don't want, the phase I want cannot occur if it's anomalous, and if it is allowed, then it should occur. I don't find that very persuasive, and it doesn't also address the question whether that means that all possible chiral gauge theories can be obtained this way. You know, can I do an E8 gauge theory, chiral gauge theory? I find that without the dynamics being somehow connected to the anomalies in a clear way, I don't have much of a road map for what's possible and what's not. But this might give me my own limitations.
Okay, thanks very much.
I have a comment, David.
Yes.
Professor David Kaplan. A very wonderful talk. I think one more perspective other than the one you mentioned. I think you mentioned 3 of them about how to get rid of mirror fermion, and the last one is about by introducing interactions or proper interactions. There's actually another view to look at this problem is that you don't even start from a gapless mirror fermion, but try to introduce a symmetric gap boundary. So there is no problem of dynamics if that's possible. So the question, let me state again. Usually people say that let's put system on some finite dimensional Hilbert space, some regularized lattice, and there is some chiral fermions on one side if they're one edge, one boundary, and there's some boundary on the other side, and there is some fermion doubling. And that's how people look at this. And then you try to introduce interaction. And there'll be issue about dynamics, and people worry about this. And David Tong makes some progress, maybe from Susi gauge theory, etc. So these are the perspective that you mentioned from introducing interactions. But the thing about checking the anomaly matching is actually saying the following: if all the anomaly, including perturbative local and non-perturbative global anomaly, are all matched, the question can be phrased to the following: is it possible to have a symmetric gap boundary between one phase that you are checking with the anomaly and the trivial vacua? But almost by the understanding of the classification of phase, it just means that if the two theory really have no distinction and there's no any subtle observable you can find on the boundary, then there should exist a symmetric gap boundary. It just means the two phase can connect to each other. I don't know whether this message is clear. So the classification of anomaly phrase in terms of classification of phase, invertible topological phase actually, in one high dimension, suggests no anomalies actually there exists a symmetric gap boundary connect the two vacua. One vacua on the co-phase A, trivial vacua. The other phase is the vacua that you construct the lattice model. Suppose these two phase A and B can connect, then there must be a symmetric gap boundary. So if one can start from construct a lattice with symmetric gap boundary, then you already get rid of no mirror fermion to worry about. That's just a symmetric gap boundary. And the other side will be the chiral fermion. It's easy to say, but this is the idea. And I think I agree with you, the construction for the precise regularized chiral fermion wasn't being complete. I think Xiaogang may have a different perspective, but to me, the missing link is how to construct this symmetric gap boundary from the given data of the maybe some symmetry group like spin 10 or some SU5 with some maybe Z4, etc. Given this data, can you construct symmetric gap boundary? That part, I think, to construct this non-perturbatively, maybe there's some mathematical things get involved. I think, in my opinion, some geometry topology type data that I need to sort out. Yeah, but and then the punchline is that I'm trying to provide some perspective without going through the difficulty of dynamics, going from gapless phase to a gap phase. One can just start looking for the symmetric gap boundary gap phase without even start from the gapless. I don't know whether this message is clear. And this may be not the mentioning your 1, 2, 3, but something like 4. And actually, that's a perspective. I think in the new paper I write with Wen in 2018, the abstract we say by the existence of a symmetric gap boundary. So there we are not trying to gap the mirror fermion, but by the existence of symmetric gap boundary, then one can say there should be a regularization. And yeah, but I agree with you. There should be more work to done. I think there's some hidden mathematical beauty there. It's my take. I think Xiaogang take it differently. He probably want to view this as introduce some random Higgs field. Yeah, and that perspective I don't think particularly beauty or insightful, but that's the story I think he take, and I take a somehow slightly different perspective. So that's my comment. There's some false view about the mirror fermion. You just introduce some symmetric gap boundary without breaking any symmetry. Yeah. Without breaking the required symmetry you want to gauge later. So then the word you start with is just already have a chiral fermion. Let's say in 3+1D, or you don't even have a finite width that can be truncated, and there's just a symmetric gap boundary directly connect to the vacua that's trivial. So the trivial vacua 4+1D is nothing. You can just remove it. Anyway, thank you.
I wish I could get in front of a blackboard with you for a couple hours in person, but
yeah,
maybe in the future.
Yeah, maybe we can do that at some point. Yes, I do.
I hope so.
Yeah, cool. Thank you.
Yeah, thank you.
Actually, I'm thinking, let me see. There's just one comment. Since David is here, I think we can invite David to give a talk again at CMSA about his recent work on this gap chiral fermion. I think there's another person's, what's his name, in the Syracuse. Simon or Simone? Maybe someone knows. The Syracuse University. There's
Simon Patterell. He was here at the talk. I don't know if he's still here now.
Yeah, so I think he can also speak. Maybe we can organize some seminars here and invite people to speak. Anyway. Well, thank you, David, for the nice talk. Thank you.
So any more questions? If not, let's thank David for the beautiful talk again.
Thank you very much for inviting me. Quite an honor.
And thank you all for joining us. Hope to see you next week.
Thank you,
David. I really enjoyed that.